not an R, but it's a D. So what I've drawn here is some leads leading out, because I want to find out what is its respective voltage. So there's a voltage distribution for that resistor and that conductor. So for this, the voltage will be using a Ohm's law, V is equal to IR. So the current that's going through it is IC. This one is actually a time-varying current. Now, why time varying? Because this is providing your PWM, your PWM signal that is time varying. It depends on each point of time that you have what kind of power. So that's the voltage across this, and the voltage that's across an inductor. Now I hope you remember that that is equal to L, which is your inductance, I dt. Right, that is your voltage across an inductor. So altogether, this voltage over here, that will be RIT plus L DI dt. That's the total voltage. So if I were to consider, let's start by considering the armature voltage. For the armature voltage, as we have seen before, this is Vt minus Et, where this one is your back EMF, for your back EMF. This one must be equal to Vt minus Kv theta dot T. How do I get that back EMF? If you were to recall, because Et was Kv, so this small letter k, or capital letter K, I put this part over here. 5 omega T. That was your back EMF that you saw before 2 lectures ago. And this Kv5 will stay, and this omega is actually your theta dot T. And omega is the same as theta dot. And this one is the same as capital letter K, V, theta dot T. So that's how your back EMF got to this. So this whole thing must be equal to this part over here. Right? This whole part over here. Because that's your total voltage. So they must be equal to each other. So I can re-express this into Vt minus RIT minus L di dt minus capital Kv theta dot T equal to 0. So that was the equation that was provided in your set of notes. There isn't really much explanation, so I'm just filling in the gaps. So what we do next is to apply the Laplace transform. And I'm going to use this L symbol to represent Laplace transformation. It's a shorthand. So if you apply Laplace transformation to the above, I'll just write at the sideline, recall, if I have Laplace transformation of x, I get xs. The Laplace transformation of x dot, I get s, xs minus x0. Laplace transformation of x dot dot. That will get me s squared x s minus s x naught minus x dot a quick revision of that Laplace transformation equivalent. So I'm going to get use of that. So my v t will become v s, and that r will stay because it's constant. I will become capital I, and this whole part over here, L S I S minus I naught or minus KB S theta. Running out of space, I'll make this off a little. This is a symbol for my capital letter theta. In your set of notes, it's kind of like written in that way. I have no time to write that. So S minus theta naught is a small letter theta and equal to 0 after the Laplace transformation. Now the initial condition says that this part is 0 and theta at time 0 is equal to 0. Right? That's before your model gets started. So because those are 0, I'm able to simplify it to Vs minus Ris minus SLIS minus S Kb capital theta s equal to 0. So I'll call this equation 1. The next thing I want to do is to consider the output of the mono shock. Now, I want you to recall again that torque is equal to small letter kt by I, and I had this written as capital KT I, where this I now is time variable. So I had solved this before. This one came to the top of the motor, right? Tm equal to KT I with time. I is time variable. So this one is equal to J theta dot T plus dm theta dot T. What are those J and the T? Previously, I'll just write this. Previously, it was written as I, and this one previously it was written as V. So this one is for your motor and load inertia, and that one is for your viscous damping. Coefficients due to your friction and again for motor and load side. So previously it was V and I over here for inertia and damping. I don't know why the set of nodes by Glasgow they changed it to J and D. Right? Probably because it's total. So as a total, write either capital J and capital D for it. So we have this form, and we could apply the Laplace transformation. And Why are we doing this mathematics? Because we are trying to get the relationship of the load position, which is going to be defined by your feeder, to the armature voltage, which is going to be defined by the V, this V over here. We're trying to get that transfer function. So if we were to apply the Laplace transformation, that K, T there will stay, I will become capital IS. And this part over here, because of theta dot dot, so it becomes S squared J theta S, plus this part over here becomes S Vm theta S. So where a lot of it will be equal to 0, the initial conditions. This one is equal to 0. That's why after the Laplace transformation, it doesn't appear over here. Your theta dot is also equal to 0. So it's simplified to this form. So I can express IS as a subject, 1 over KT, and the rest of it. And I call this equation 2. So what we need to do next is to substitute 2 into 1. So IS substituted into equation 1 over here. And over here. So there are 2 IS over there. So I'll just sum it up already. I'll just put them together, bring out the common factor IS. So if I were to do that, it will become BS equal to minus R plus SL over this factor KT S squared J by the figure S plus SDM figure S minus SKB figure S equal to 0. Just substituting it and doing a little bit of simplification.
Wow.
So there is this inductance term over here. So what I'm going to do is to neglect this small amount of inductance. So neglecting that L, that inductance. So the whole thing now becomes Vs. And I'm going to take that common factor theta out. Right, that common factor, I'll take it out. And this term here becomes 0. And eventually I could form that equation of theta S over Vs in the following form. 1 over R J over KT S squared plus 1 over J S dm plus KT RJ S dv. And this one, I can multiply a factor of KT over RJ at the top and the bottom. KT over RJ. Multiply it that way, so I get KT over RJ. Divided by S dn over J KT dv over RJ. So what I've done is to find out what's the load position to armature voltage transfer function. That's why you learn your dynamics control, so that when we come to this transfer function, then you can make use of the transfer function to do your control of the motor. Now this transfer function was set up without gear, and the next set of notes over there goes about trying to find out what is the transfer function when there is a gear reduction system coming in between your motor and your load. There's a gear. So this is the system over here, where you have your motor. It looks very familiar to you because you've seen this before. And then there's this gear reduction, and then there's the inertia and the load, and then the load itself. And then there is the position that you want to find out. What we are after is this one wrong. It's a load position to armature voltage. Low position to armature voltage. Why not armature voltage to low position? Because it's always output divided by your input. In this case, your output will be your low position, and then your input here will be your armature voltage. So that's the new part over here compared to the last example over there. So let's have a look at how do we go about solving it. So there's a gear reduction ratio over here. What we want is the control output actuator position, so the low position. And then we use this input, control input, as our motor armature voltage that's going into the motor. So for this, what I'm going to do is do the same thing. I'll have some mathematics given over here. You'll see that you can choose to write after me or just fill in the gaps, some of these gaps over here. So, summing up the torque is equal to I here dot. We'll start with this. On the motor side, so for the torque of the motor, we have seen before is Tm minus TL over N. That's 2 lectures ago, so I'm just writing down that plus dm equal m. So again, this dm is your viscous coefficient of friction. So it's sort of like damping. And this Im over here will be your motor inertia. So I could readjust this whole thing. Tm equal to Jt now. Here dot m plus dt. Here dot m plus TL over n. So this part here is your total inertia. And that part there is the total damping. So total means motor plus the load. Here as well. So both motor and the load side, the inertia and the amount of damping. So So where in this case your dt will be equal to dm plus dl over n squared. What you've seen before, jt im plus il over n squared. Now I know that previously 2 lectures ago you were using capital I, but now the set of notes, I don't know why they want to use j. So to be consistent, I'm using j as well. So apply the plus transformation to this set of equations over here. The theta dot dot and the theta dot under 0 initial conditions. I'm just going to write down that one under 0 initial conditions. Tm will be s squared jt, theta, the letter theta m, s, plus s dt, theta s, and then plus tl over n squared. Taking the Laplace transformation. So there's a common factor, theta m, s. I'm going to take that one. So Tm minus TL over n squared. There's no square. There's no square. There's no square. And then the denominator s sjt plus dt. All these equations good. Next thing we need to do is to write down the control block diagram. Now you have already learned how to convert a transfer function into a control into a block diagram. There are different ways of doing that. The way that I'm doing maybe using the fundamentals. I'm trying to write the control block diagram of this transfer function over here. So I know that n is equal to r L over Rm. This is also equal to theta m over theta L. N is your K ratio. So that means 1 over n is equal to theta L over theta m. Just a side line. So what that means is this is gain equal to output divided by input. So I can sketch this sort of thing in that way. 1 over n, output will be theta L, capital letter theta L, capital letter theta M. Right. How I got this is because this can be transformed under Laplace to be 1 over n equal to theta L, theta M. So if I have this, then I could establish my control block diagram. I have this as 1 over n, theta m, and theta L. And the rest over here, that will be this denominator, 1 over s sjt plus dt. in as positive, and then that TL over n as negative. So that's the part of a block diagram. It's not finished yet because I'm supposed to relate the load position to the armature voltage. So there's still going to be a little bit more. Now, in a set of notes, it jumps immediately into that final sketch, but I'll give you a little bit more details how I will be doing it. Just a little bit of revision. Tm is equal to capital K T I. And I is equal to V minus kV omega divided by R. Now this had been solved before already in the past, so I'm just rewriting it. This part came about because of the back EMF. And a few other things to recall. Tm equal to K T over R, so V minus kV omega. And I can change that omega into theta dot. Omega is just like theta dot. So that will be equal to KT over R, V minus kV, and that theta dot is the same as N theta dot L. That's because just now we were talking about theta L over theta M is equal to 1 over M. So I'm just changing that. So theta M, theta dot M into this form over here. So I'm going to write this down. Tm equal to K T R V minus K V N theta dot L T. And applying the plus, I get Tm equal to K T over R Vs taking the plus and I call this equation 4. There's one other thing. Also, we'll assume the torque seen by the motor due to load is negligible. So if that's the case, if the torque seen by the motor due to the load is negligible, that means my theta M is equal to Tm, so that load, that torque on the load side will be gone. And you get this expression that we call equation 5. Now this theta M is the same as N theta L. Equal to this form. So I could re-express theta L as equal to 1 over M Tn as SJT plus T. Equation 6. after you have all these expressions, you're going to sketch the overall transfer function. So we already have that part. I'm going to sketch out 1 over S plus JT plus D. Either M, 1 over N. I think it was last year that this question came out as one of the exam questions, asking you to prove. This part here, Tm. I'm using all those equations that are out there. Kt, input for that is I. Over R. You have your voltage. Plus. And this one will be VE. That's your back EMF voltage. KE. Omega N. S. The wrong side. Now you have learned before in dynamics control how to draw your clock diagram. So we'll be using that same technique in VDC as well. I'll just help you a little bit on this part. We know that back EMF is equal to the following. So if I take the Laplace transformation, it will be V E S S K E S. So your S theta M S will be equal to VE S over KE. And actually this is actually equal to omega M. So S is equal to omega M over here M S. And VE S KE is equal to K. Is that right? It's your omega That's how we got this feedback side. It's not done yet. From equation 6. Equation 6. Either L S equal to 1 over N Tn over S SJT plus T. What we need is to substitute 4 into 6. Substitute equation 4 into equation 6. So I'll have either L S AC over NR, GS, TV, N, here L, S. Divided by S, S, T, T. I can simplify this. And multiply this out. And bring the other term over. This N and that N will cancel out. And as a common factor, theta L, I'm going to take it out. Just taking out that common factor. And eventually I could form the transfer function. Theta L S over Vs. That will give me the floating form. By this whole thing, denominator. So I want to put some meaning to all these terms over there. So this one here will be your motor of constant. It has the units of Newton meters per ampere. This R over here is your motor resistance. It has the units of current. This one over there is your motor voltage constant. It has the units of volts per radians per second. That thing there, that's the total damping, that's what we've seen before. And the units newtons meters seconds per radian. That's because of the location. And this total damping is seen at the motor site. Seen at the motor site. JT over there, that's your total inertia in kilograms meter cube. Again, seen at the motor site. And you know already that's your reduction gear ratio. So Vs there, that's your input armature voltage. That one there, that's the load, output load. Position. Let's have a look at an example. Before looking at an example, I just want to walk you through how we energize the motor. If we look at the speed versus time, there's an acceleration phase, constant speed phase, and then deceleration phase. Energize and then de-energize the motor. So the amount of torque that applied to it, you start with a step size torque, and that step size torque is going to accelerate the motor to a certain value, and that later on we'll be able to calculate what that value is. Now, at a constant velocity, that's where you do not need to apply any torque at all. So the torque that's applied by your motor essentially is zero. And when you need to decelerate that, that's when you need to have this braking torque that's applied to it. So the braking torque is just applying torque in the opposite direction. So that's why you have this drop. So this torque is the deceleration torque. That torque over there is acceleration torque. So if you want the motor to ramp up its speed, it's not to apply a torque that ramps up. You apply a constant torque. So applying a constant torque, the motor will start to ramp up gradually. And as it ramps up to the level that you want, then you will stop applying that torque, zero torque, and then the motor will maintain that constant speed. And when you want to decelerate that, that's when you apply torque in the opposite direction, and you will decelerate. Now this figure over here is when it's a purely inertial load. If you have the initial load plus a fixed load, that means over at the load side, not only you have bring you back to this figure. Not only you have this, but you also have this. That's where your load is. This is where your inertia is. So if it's purely inertia, then you have the first case that I was just talking about. If you have that inertia plus this load, then you will see you'll be looking at this second case over here. Inertia plus fixed load, where not only you need to accelerate it, but you need to supply the amount of torque to overcome the load. So that's the combined total torque that you need to apply, both to accelerate it and to drive that load again of the motor. After you supply that, you run it, and then you accelerate. And when you want the constant speed, that's when you drop back to supply the constant torque to overcome the load so that you can maintain that. And when you want to decelerate it, that torque, decelerating torque, is taking that load minus that deceleration. So TL is this value over here, minus T deceleration is that amount. So T deceleration is equal to T acceleration. That's provided that the time for acceleration and time for deceleration they are equal to each other. So this value that you apply will be equal to each other. There's one year that the question says that this deceleration is different time compared to the acceleration time. So that means this slope is steeper. There's one question about that. But the following example, this example over here, shows that it's equal amount of time. I'll try to solve it so that it allows you to do your retard as well, which I'll be uploading after this lecture. In order to solve this question, I'll do a very, very simple sketch. You have a diameter of 10 centimeters, and that's your motor side. It has a concentrated mass of 1 kilogram, and it's driving the reduction gear. Rotate, n is equal to 10, that's given in the question. So after that reduction gear, it goes to drive this concentrated mass, 2 kilograms. That is 30 centimeters away from the axis. So the torque by the load is given as 2 newtons meter. And it asks you what is the torque provided by the motor. With the hope to achieve this kind of a characteristic for the motor, that initially you will have 0.5 seconds of acceleration and maintain a constant velocity, and then another 0.5 seconds over here of deceleration. So there was one year that the student thought this 0.5 seconds is from this 0 point to this point. It's not. It's just that deceleration phase. That's 0.5 seconds. And that constant velocity will be 2,000 RPM. So let's have a look for the load, JL. The inertia for the load will be given as ml squared. M, where the load side has concentrated mass, 2 kilograms. And L over here would be 30 centimeters. Convert that into meter. So you get 0.18 kilograms per square. How about looking at the motor side? Jm. On the motor side, is half mr squared. So half the mass is 1, and r would be 0.05 squared. Because that's the radius. The diameter is 10 centimeters. So this one would be 0.00125 kilograms per square. Let's have a look at the load inertia seen by the motor. So JML equal to JL over n squared. Load inertia seen by the motor. 0.18 divided by 10 squared. 0.0018. So the total inertia seen by the motor now will be JT. So JT will be Jm plus JML. Will be 0.00125. That one we saw over here, Jm for the motor, plus the one that's seen by the load inertia seen by the motor. That's 0.0018, and I get 0.00305. So for the acceleration of the system, that is acceleration equal to omega f over t. This omega f is the motor speed. So you have 2,000 RPM divided by the time that's required, that's 0.5 seconds. 0.5 seconds. This is RPM. So in order to convert it into radians per second, I just kind of have a side line over here. RPM is revolution per minute. In order to convert into radians per second, radians in seconds, what I need is that there's 1 minute over here, so this minute and this minute will cancel. Revolution and revolution will cancel. So what I want is that 1 revolution is equal to 2 pi. And 1 minute is equal to 60 seconds. So I have this vector, 2 pi divided by 60. That's how I go about doing my units conversion. And if I work it out, that will be 418.7 radians per second. So that's for the acceleration phase. For the deceleration, and I'm going to use modulus D to represent that, because you get a minus value, but I know that it's deceleration. So that will be 418.7 radians per second. That's because deceleration also requires 0.5 seconds. So now I have that motor torque required during acceleration as t equal to j t multiplied by acceleration plus TL over n. That's torque. So 0.00305, that one we've seen before, 418.7, that's 2 over 10. So I get that torque as 1.48 newtons meter. So that's for the acceleration phase. How about the motor torque for the constant speed? In a fixed speed, you don't have that acceleration part, so it's only TL over n. That's 2 over 10, 0.2. And for the deceleration phase just means that there's a negative term over here. So motor torque during acceleration, t equal to TL over n minus j t multiplied by 8. This is kind of like the deceleration, that minus a means deceleration. So that will be 2 over 10, 0.00305, and 418.7. Do that calculation, minus 1.08. So I can now sketch the entire torque response. I'll have that first one, that is 1.48 newton meter. And that one will come down to 0.3. At constant speed, so you will go backward. And for deceleration, it's going to come down to this level. That is minus 1.08 newton meter. It is carried on for 0.5 seconds. And this one is for 0.5 seconds. Now there's one here with a little bit of extension talking about efficiency of the motor. So a lot of students couldn't do that part. That's because it wasn't really, there wasn't an example about that. So what I'm going to do is to give you just that little bit extension. So I'll give you the case if efficiency of the motor is 85%. And I want to find out what is the power of the motor for the acceleration, deceleration, and constant velocity phase. Acceleration, and constant velocity phase. Like that. What will be the motor power output? The motor power supply is actually equal to the motor output divided by the motor efficiency. The motor power output is equal to speed multiplied by torque. So that is the relationship. It's also provided in your notes, but they didn't really give an example. So I'm giving that. So in the acceleration phase, the PM supply with 85% efficiency, that speed would be 2000 times 2 pi divided by 60 to convert it to radians per second, multiplied by torque 1.48 and divided by 0.85, that's 85% efficiency. So that power is 364 watts. In the constant velocity phase, constant speed, that PM supply is just doing the same thing, but with different torque. So in the case of constant velocity, that's 0.2. So I get that as 49 watts. So the same for that deceleration phase. PM supply equal to 49 minus 364. So instead of calculating, I'll just take 49 minus 364. So that will give me minus 3.6 watts.
Oh, fuck. So
I can sketch out that power consumption. This one is power in watts. So it starts from 0, it goes up all the way to 364 watts, and then you come down as a power consumed to this level at constant speed. This one is at 49. And for that deceleration phase, this one here is at minus 3.6. So again, this is 0.5 seconds, and that is 0.5 seconds. Alright, that's just the extension part of it. Next week we're going to path planning, and I'll still have 2 more lectures with you for path planning. Classically, path planning question, all students attempt it during the exam, because that part is a lot more easier. So I'll see you this Friday.